Okay, time is 11 o'clock, so let's begin here. So assignment number 3 is due on Friday at noon. I will do my best to try to grade that and give it back to you before the midterm. At the very least, I will post an answer key to the graded materials webpage, and I'll of course let you know if it's posted there and I am unable to grade the assignments. So midterm is on Tuesday. We will actually discuss that in about 10 seconds. Are there any questions? Okay. So originally I was going to discuss the midterm at the end of class, but I decided to change the ordering, and we'll discuss the midterm first, and then we'll address, leave it open then for questions, and then we will start going over the parallel processing section again. Okay. So we will begin at 11 a.m. as you might expect, and I think as I mentioned to you before, the exam is actually an hour and 15 minutes, but I'm going to give you an extra 15 minutes just in case you need it. So we will go until 12:30. Okay. Make sure you're familiar with how to use these computers here, and as was just revealed before class is that for some reason our logins are not working on these computers today. I had actually checked these computers, I think it was last Thursday or Friday, and they were working. So I don't know what has happened.
They worked on Tuesday too.
Okay.
I was able to log in on Tuesday.
Oh, good, good. Thanks for the information. I will contact the appropriate people to find out what's going on. Either we get these computers working, or you're going to be having to do Monte Carlo simulation by hand on the exam. So let's get these computers working. Also, does everyone remember how to log on to these computers? You do not use your Blackboard ID. Does everyone remember? Does anyone need me to tell you what the login and password is?
Let's just review it so I can write it down.
Here's the login. The first letter is not capitalized. Well, it might look like it. S-StatLab. And then password HH stat 2 exclamation marks. You know, 1 minute before the exam, don't say to me, how do you log into these computers? Don't say that to me.
So H is capital or?
The H's are capitals. Hardin Hall, stat, and you're very happy. The formula sheet for the exam is available on the graded materials webpage. I'm not going to print that out. You can open that file up as needed during the exam. The exam covers obviously the Monte Carlo simulation section and the boot part 1 notes.
It's over here.
It did. Interesting.
No? Okay. Why don't we just try? Maybe it was just momentarily down. So if you could just try it on your computer real fast. Ever since I started doing these computer-based tests back in 2006, everything's always worked out, but there's always a fear.
Yeah, it works in.
Okay.
Or it's thinking about it. It didn't give me this is locked.
Okay.
Go away.
If you don't if it doesn't eventually log on, let me know. So I've always feared that a disaster will occur, and that, let's say, the internet will be down, or the computers don't work for some reason. Fortunately, that's never happened. Let's hope it doesn't happen again, or it doesn't happen as well. I once did have the fire alarm was set off during an exam. I think that's the closest I've ever come to a disaster.
What did you do? That's like.
And we were in this
15
building,
minutes.
we all walked out that door, so I could obviously keep track of if people are communicating about the exam or not, and so I just then give more time. So the Bootstrap Part 1 notes, but to give you a break, not the Bootstrap Part 2 notes. Okay? So no regression. Obviously, your assignment does have a little bit of regression on it, so I'm still evaluating you to some respect on that set of notes, but it won't be on the exam. This is how the test stands right now. I might make one minor change. I might make one minor change to it, but it won't differ too much from its current format. So it's 100 points. Problem number 1 is 34 points. And you will have to do a Monte Carlo simulation, set of simulations. So you're going to use R for that. For some parts you won't need R. You'll be basically interpreting some of the results that you got. You will be working with some simulated data. To help you out, what I will actually do is post to my course website shortly before the exam starts a program that contains the code for how to simulate the data. So you'll download the program to your computer and simply run the part that simulates the data. There will also be other components of this program that I've set up to do that you will use for other problems to help you get stuff done quicker, rather than, let's say, me maybe showing you how to, simulate the data on the tests, and you would have to type it in. Instead, I've typed it in for you. You just have to download it and run it. Okay. I've also given you some check values to make sure that indeed you have simulated the data correctly. Problem number 2 is worth 17 points and involves the bootstrap. Again, I'm going to give you now one simulated data set. I'm going to give you the code to do it. And you need to use a simulated data set to do some stuff with the bootstrap. As you might expect, given how much time we spent on it, you're going to find a confidence interval. Okay? Number 3 is worth 12 points. It's going to be on the bootstrap. But no, you don't need to use R for it. Number 4 is worth 16 points. Monte Carlo simulation. And you don't need to use R for it. So you might be thinking, okay, well, how can I ask you questions about the bootstrap and Monte Carlo simulation when you're not actually using R? Think about it. And then lastly, number 5 is worth 21 points. It's 3 short answer questions that are not connected in any way, and there's no R associated with it. If you've had me before for a class, it's the usual type of questions I have at the end of all my tests. If you haven't had me for a class, I will actually give you an example of one in our test review. And also, I guess there is a problem number 6, 3 points extra credit. Okay, so that's the general layout for the exam. Again, like I said, it may change a little bit. There's one small part I haven't decided upon yet. Okay, so overall, I don't think the test is hard, but then again, I'm the one who made up the test. Okay, and as again, if you've had me for an exam before, you're going to hear some similar stuff to what I've said about my test before. And first of all, there should be no surprises on the exam. Everything on there you have seen before. It basically comes down to, have you studied enough? And I often, unfortunately, do have students who do poorly on my exams. And they come talk to me after the exam, they want to discuss it, and they very often say, well, yeah, I remember us going over that. Obviously, though, I didn't understand as well as I should have. So, there is, everything that we discussed in our class is fair game for us. Just realize that everything is fair game, unless I have said, don't worry about it. Okay? Common issues that students have on my exam and where they miss points is that, one, they might not answer all parts of a question. So for a very basic example, suppose I have you calculate a confidence interval for something and say interpret it. Well, a student will calculate the confidence interval and then forget the interpretation part. Depending upon how the problem's structured, that might be half credit. Half of that points you have just lost. So make sure that you understand what the question is asking and you answer all parts of it. Also, another problem that sometimes students have is that they actually answer the wrong question. So I was trying to think of an example with respect to the material that we've talked about, and I found it kind of difficult, but this was the best one that I thought of. Suppose I asked you to use a jackknife to estimate a variance, but instead you use the bootstrap instead. Okay? Well, it's very hard for me to give you a whole lot of credit if you've just essentially answered the wrong problem. Those are the kinds of issues that I see most of all with students taking my exam, and that can cause grades that are not necessarily desirable. Also, with these exams, you need to be very proficient in your R coding. You only have an hour and a half to take the exam. If it takes you 15, 30 minutes to write like a calc.t function, that means that you do not have as good of an R background as you should. Okay? I guarantee you, at some point in the exam, you're going to write a calc.t function, similar to what we've done in our class. The statistic that you're going to have to calculate, or statistics that you're going to have to calculate, will be very simple and should take you 2 minutes, 3 minutes at most. But if it's taking you 15 minutes or more, that tells me then that you don't have enough of an R background to do this stuff at the level that you should for this class. So what I recommend to you as a way to study for the exam, pick your favorite statistic, write a calc.t function for it. Get your next favorite statistic, write a calc.t function for it so that you can practice doing that. Take some simple statistics, write it up so that you can use the boot function with it, or you could do simply Monte Carlo simulation with it. And that's a way to practice to make sure that the very basics of using R you have down. And it's not something that's going to take you 15, 30 minutes to do that. You can do it quickly. In terms of the test structure itself, as I've said before, I will give you a paper copy of the exam, and you'll have to write all your answers on that paper copy. You will use the computers that are in front of you to take the test. So these computers essentially serve the role as almost like a calculator for you. So maybe you have to write a little bit of R code, and you get a numerical result. You put the numerical result on your test. But also, you need to show your work in some way. So if I ask you to find let's say a basic interval, basic bootstrap interval, okay, don't just put down, something like 2 is less than theta is less than 3. Okay, you need to show your work in some way. So how could you show your work? Well, if it's a basic bootstrap conference interval, you could include t. You can include the actual quantile that you may need. You can write it out like this in terms of a formula, and then actually give me the actual value. Actually give me the actual value there too. And that's how you show your work. Now, obviously, there's some variability in terms of you could say how much you would show your work. But I need to see something, because if I don't see something, it's very, very difficult for me to give you any partial credit if you wrote this here and this was wrong. Because what you could have done is maybe guessed. Theta is between 2 and 3. Okay. When in fact maybe you made a very simple calculation error. Another way that you can show your work too is to show me some of your code. Now, I don't expect you to show me 10 lines of code, but if you're doing a basic bootstrap interval, what you could do is say, well, I wrote a calc.t function, and depending upon how much time you have, you may or may not put stuff there. But at least I understand you know the process, and you use the boot function. You could put some of your arguments in there as well, and then maybe use boot.ci, for example. If I see something like this and you got the wrong result, that tells me, okay, you know the process to do it, but there's probably just some small mistake that you made. This is what I mean by showing your work. Again, you have to take into account too, you have an hour and a half to do the exam. So, you might be, the first time through the exam, you show your work a little bit, and then you say, oh, look at good, I have 15 minutes left. I'm going to go back and show some more work. That will be one strategic approach. If a problem doesn't, call for using R, you can still show your work in a variety of ways too. I guess now this is backtracking a little bit. Let's say I asked you to find a true confidence level for an interval. Well, you know how to do that in R, but make sure this is where you can write out the corresponding formula that you would need to do the true confidence level, and that tells me, okay, you know what the formula is. Again, just some small calculation error probably occurred. That's one reason why I give you the formula sheet too. Let's see now. Now on these computers here, obviously there's R. There's RStudio, but there is not TIN, but there is RStudio. So you could use that. You can actually use the program editor that comes in R itself. In the end, the programs that you're going to write are rather small. So again, you only have an hour and a half. So maybe the program editor in R itself will be fine. I would use RStudio. Yes.
Will we have to download any packages, or should what we?
I am 95% confident for this exam you do not need to.
Okay.
Let's see. Also remember that this is closed book, closed note, this exam, but you do have access to my computer programs. So you can look at any of my computer programs that are available online. Obviously, too, since you're using a computer here, this leaves you open to other ways to get help, such as communicating with your fellow classmates via the computer. That course, is not allowed. Please make sure that your computer itself, you keep your eyes on your own computer. Don't look at the computer that's in front of you. Make sure that you're using a reasonably sized font. Don't use extremely large font. That makes it easy for the person behind you to see what you're doing. And lastly, also in case you are not aware of this, I can actually see what's on your computer screens up here. Okay, so there's really no reason to do something that you shouldn't be doing. Okay, so that's the general layout for the exam and gives you an idea of what to expect next Tuesday. Next, what I'm going to do is do a review of some of the material. Do you guys have any questions, though, before I start this review of material? Okay. So, we began with Monte Carlo simulation. Well, understand the basic definition of what I mean by simulation. What we're trying to do is use a computer to repeat some process over and over and over again. One of the first things that we talked about in this Monte Carlo simulation section was what the EDF is. Make sure you understand the definition, how to find an EDF, and why someone would want to look at an EDF. And what we're doing with Monte Carlo simulation is, as estimating expected values. That's basically what we use Monte Carlo simulation for. And what's probably most important typically for statisticians is that you're in a research setting, you're trying to estimate expected values. Why does Monte Carlo simulation work? It all comes down to weak law large numbers. Everything's coming from there. That's why we can do what we're doing and get good results. And then we looked at 4 different typical ways that Monte Carlo simulation is used for statistical research. Typically at the end of all statistical research papers, you have a section called simulation, for example, and where someone uses Monte Carlo simulation to evaluate their statistical method proposal. And so we looked at 4 main ways that this is used. The first way is to get at, let's say, approximate unbiasedness of a statistic. And so we talked about an algorithm that one could use to get at the approximate unbiased of some statistic, let's call it T, or how to evaluate that, I should say. Make sure that you understand how to implement it in a test-taking situation. I would not give you any really complex statistic to look at in a test-taking situation. But I could ask you to do some Monte Carlo simulations to evaluate it. Make sure you understand how to make judgments about unbiasedness. Take into account simulation variability, for example. When you're making that judgment, we even found out like a confidence interval to help evaluate unbiasedness. Then we looked at true confidence level and expected length. We make sure that you understand the relationship to what we're doing with number 2 with that weak law large numbers. Understand the corresponding algorithm that I gave you to make this judgment about true confidence level, and does it match up with the stated confidence level. Similarly, how to estimate the expected length. So the algorithm, make sure you can implement it in R. Understand what a conservative interval is versus a liberal interval. how would you choose between two intervals? Then third, we talked about the size of a hypothesis test and the power. How to estimate those quantities with respect to hypothesis tests. Make sure you understand how to do that. It's a relationship with the weak law of large numbers. Make sure you understand the algorithm, how to actually implement it in R, and then how to make decisions between, let's say I have two hypothesis testing procedures. One, let's say, has an estimated size of 0.06, another one's 0.15, where the goal was alpha equal 0.05. Well, which is better? Well, the one, let's call this 1, let's call it 2, the one with 0.06. Let's say that this was for size, and then for power, let's say in one set of simulations you got 0.7, and you got 0.6 here. Well, which of those methods are better? Well, just because this is higher power does not mean that this is a better method. The reason being is because it doesn't hold the correct size. The reason why it's rejecting more than this one is because it rejects too often when you know that HO is true. So you would not pick method 2. And then lastly, we looked at the approximate unbiasedness of a variance estimator. Remember, that was a little bit more of a complicated algorithm. Make sure you understand all parts of that algorithm, how to actually implement it in R, and understand why the algorithm works. Again, I think of all the 4 algorithms, that was probably the most difficult, but in the end, once you see it, it's like, oh, okay, yeah, that makes sense. Or at least it should make sense. Make sure you're familiar with it. Then how to actually then interpret your results. So if you remember, we calculated a value called W. What are we looking for with that value of W to decide, well, is this a good estimator or not? Then we spent a lot of time talking about simulation variability and understanding it. I kind of discussed that before. And make sure you're familiar with, again, if I have an estimated true confidence level of 0.04, and my goal was, or my stated value, estimated true confidence level of 0.94, and my stated confidence level is 0.95, how do I know if I'm close enough to say, yeah, everything's probably okay? Well, that's what we talk about for simulation variability. Then that gets into also, how do you choose R, where R is the number of simulated data sets. So we looked at some techniques, I guess you could say, for how to make that choice. That also people often choose an R that's too large, actually. We talked about estimating the time needed to do a Monte Carlo simulation as well. This is a very good planning tool. We talked about plots that can summarize our simulation results. What I could do on a test is actually give you a plot. Maybe take one from one of my old research papers, give you a plot and say, okay, tell me which method is best. You don't necessarily need to understand what the methods are, but just tell me, based upon this plot, maybe it's of the size of a test, tell me which method is best from looking at this plot. And then checking for errors. And whenever you're doing programming, you have to worry about, well, did I program it correctly? And so, let's say that, you're getting, maybe it's an estimated true confidence level. Let's say for, n equal 100, you get an estimated true confidence level of 0.9 when the stated level is 0.95. You present this to your advisor, and your advisor says, Are you sure you got it right? I would have expected that it would have been already about 0.95. What would be one of the first things that you could do to check to make sure your programming is right? Increase the sample size. Exactly. Now, that will be for like a method that it depends upon as n goes to infinity, like so many of our methods do. Find a sample size closer to infinity. See if it works. If it's not working and you keep on increasing n over and over and over again, then he's like, uh-oh, what's going on here? Maybe now my code is actually not correct. So that's always a quick way to determine if what you're doing is correct. The quickest way. Depending upon how long it takes simulations to run once you have a larger sample size. Okay, so that's the Monte Carlo simulation section. Then we got into the bootstrap. Make sure you understand the big picture of where the bootstrap fits into statistics. We talked about two common ways that are used to make inferences in statistics. And it all relies on getting at that sampling distribution for your statistic of interest. Asymptotics, and other ways to make some underlying assumption about the distribution of your data. And the bootstrap then gives you that third method to approach the problem. Well, what would be the advantages of using the bootstrap? Well, obviously, it does not necessarily rely on the same kinds of assumptions that some of these other methods do. It does not necessarily mean that the bootstrap will always be better, but it does give you a viable alternative that can work very well at times. Again, we talked about the EDF with respect to the bootstrap, that F hat. This is how we're taking our resamples. And this then gets into the plug-in principle, which drives everything that you do with the bootstrap and gives you some intuitive justification for why the bootstrap works. Because we know that F hat is going to be a good estimate of F, provided your sample size is large enough. And so what this plug-in principle then does says, okay, everywhere you would normally have an F, just put an F hat. That's what the bootstrap does. Then that led us into a discussion, well, what would be the actual distribution of, let's say, T star? And that led us also into talking about, well, the number of non-unique samples, the number of unique samples, and also the multinomial distribution. How does the multinomial distribution fit into what we do with the bootstrap? And then we started talking about confidence intervals. The first one that we talked about was the basic bootstrap confidence interval. Make sure that you can derive it. Make sure you can calculate it. Make sure you can implement the stuff in R. Is the basic bootstrap confidence interval a good interval? It can be at times. When should it be a good interval? What could be done to improve the interval? Remember we talked about the whole, we talked about transformations, for example, corresponding to the basic interval. Then this is when we first started talking about the boot function and other corresponding nice functions like boot.ci, boot.array. Make sure that you can implement these quickly. Again, if this is something that you struggle with, okay, what do I put for the first argument? What do I put for a second argument? If you're struggling with that, you don't understand this stuff enough yet. If I asked you to, do some bootstrapping with the boot function, it should be rather quick. You should be at a point now where you know how to do it. I'll just put this here just so that you remember, because I could imagine a student asking a question during the test saying, I can't get the boot function to work. Well, remember, of course, it lives in the boot package, and before you use the boot function, you need to say library boot before you can use it. We also talked about some stuff, let's say, outside of, let's say, doing inference. When we talked about estimating a variance with the bootstrap, well, make sure that you know how to do it. We also talked about bias. How can you estimate the bias? Normally, bias is unknown to us because it depends upon the parameter. But the cool thing is with the bootstrap, you have a way to estimate bias. And then you can take that estimate into account and come up with a better estimator. We also talked about the double bootstrap. Make sure that you know how to implement it. Obviously, I cannot ask you a question that's going to take 5 minutes to implement on an exam regarding where, with the double bootstrap, that obviously can happen because you have 2 layers of resampling there. Make sure that you understand what the double bootstrap is. Maybe I could ask you to write out the algorithm behind it. One of the things that I did after I had a rough draft of the exam is I came down here and tested the actual R code on these computers. And what I found in terms of what I had written for the answer key, and what I had found is the stuff that I'm asking you to do, everything should take just a few seconds. So don't be expecting to, if your computer is running for 5 minutes to get something done, you have a programming error. Then also we talked about the jackknife. Make sure you understand how to use it to estimate a variance. That was our primary purpose. I could ask you about the algorithm behind it as well. Remember how this is all connected with these empirical influence values, and while we didn't go into the details about how did the actual formula come about through this thing called the non-parametric delta method, so that's okay, but you should at least understand how to implement it. The EMP INF function, for example, and then the var.linear function. The second confidence interval that we looked at was the studentized interval. Again, make sure you understand the basic, how does it come about? I don't know if we necessarily had a derivation, but we at least talked about, how does this interval come about? A common problem that sometimes students have is that they forget that in your z-star calculation that you're doing here for it, that variance that's in that denominator, you need to calculate that for every single resample. Sometimes students just want to throw in the observed variance from the original sample itself and let it be constant for every single resample. And that's not how you calculate it. Also, we talked about with the studentized interval ways to potentially improve it. Like through using those transformations. Let's see. So then we got next into how to determine if a non-bootstrap method's use of a probability distribution for a statistic is valid. So for example, let's say if we had a confidence interval for a mean, what we could do is simply look at the distribution of all these z stars and look to see, does it kind of follow a t-distribution. If it does, then the regular old t-distribution based confidence interval for a mean should work well. If it doesn't, then that should worry you. The next interval that we talked about was the percentile interval. Make sure you understand the derivation. I might ask you to derive it on the test. How to calculate it. And then also its relationship with the basic interval. Remember, we had a nice little plot that kind of showed what was going on. Of course, then, there are some issues with the percentile interval. Make sure you understand how to improve the percentile interval, and that's where the BCA interval came from. Make sure you know what BCA stands for. Interestingly, and maybe I mentioned this before, in Davison and Hinckley's book on the bootstrap, which again is probably still the #1 book out there, as I said to you, I did the book review for it that appeared in JASA, and and one of the things I put in there, it was more just because it was kind of funny that they failed to do this, they forgot to do this. They never said what BCA stood for. They just said it's BCA. Well, come on, tell us what it stands for. Bias corrected accelerated. So make sure you know what it stands for. We didn't necessarily go through the derivation itself, and rather make sure you know the big picture regarding what this interval is trying to do. You know, it's trying to correct, for example, for bias that could occur. It's trying to correct for the fact that your variance itself might be a function of your underlying statistic. We also talked about, will an interval be within the parameter space? So what I mean by that is if I have a parameter of interest that's always between 0 and infinity, is my interval that I calculate with the bootstrap guaranteed to always be between 0 and infinity? We talked about the discreteness with the bootstrap. Oftentimes it's not, most of the time it's not something to worry about. The notation with the bootstrap can kind of get messy, and I've tried to do my best, since we only did 4 weeks of this, to try to avoid some of the messy issues with notation at the time, but we did spend a little bit of time talking about the two kinds of notation that mean the same thing. And then we got into hypothesis testing. You need to resample under the null hypothesis. You need to do that. Oftentimes it's difficult to figure out exactly how to do it. We've looked at some cases about how one would go about doing it. And oftentimes you just have to take it on a case-by-case basis. Make sure you understand how to calculate a p-value. Again, p-values themselves are just a measurement of how extreme an observed statistic is relative to its distribution. With the bootstrap, we're kind of making sure that you fully understood that. And we actually simulated the distribution. And we looked at how extreme is our observed statistic, let's call it t, relative to the distribution of t star. We talked about one-sided tests. We talked about two-sided tests. Make sure you understand why the particular formulas that we use, why they are actually used. You could use a t. You could also use a z, essentially the studentized quantity, to calculate for every resample. And make sure you understand how to use the boot function, which at times it's not necessarily as easy as you would like. To do resampling under the null hypothesis. And then lastly, permutation tests. Make sure you understand the difference between a permutation test and one that's done by regular old bootstrap in terms of resampling with replacement. Make sure you understand with the permutation test what we're doing is actually conditioning on some sufficient statistics that do not change from one sample to the next. Okay, a sample question that I actually cut from the exam is as follows. Now this would be one of these questions on that short answer part of the exam, problem number 5. A double bootstrap procedure is performed with R first level resamples and M second level resamples. Why is the total number of resamples R times 1 plus M? Okay, so how would you answer that? There are R resamples taken for the first bootstrap level. For each resample, there are n additional resamples taken for the second bootstrap level, producing essentially r times m more resamples. So, by counting the original resample itself, you have r plus r times m total resamples. That's how you would approach the problem. Now, one of the reasons why I bring this up is, first of all, just giving you an idea of what my expectations would be for a short answer problem and how to answer it. But also, we really didn't spend that much time on the double bootstrap. And so I bring this up to remind you that, yes, you are responsible for all the material that we talked about. And so, while the amount of time that we talked about it maybe was short, it's still a very important topic, and you are responsible for it. And lastly, I don't want you to forget about this. Remember, I have all those videos out there, so if you need to review some material, one of the first places that you could go is to relive what we talked about in class. Or maybe a test-taking strategy is, do a like what some people like. Sorry, can't talk right now. Anybody watch House of Cards on Netflix? I'm on episode 4 right now. Or actually, just finished 4. I'm going to start 5 hopefully tonight. And what some people do with House of Cards and other series like that are essentially released all at once, all the episodes all at once on the web, is that they'll do some binge watching. So, for example, my wife seriously thought about, I think it was last Friday when House of Cards came out, she seriously thought about taking the day off from work and just watching House of Cards all day long. So what you could do with my videos for this class is do some binge watching, if you want, to review for the exam. So you could do that. It's up to you if you want to do that, but the reason why I put those videos out there is because I think that can be like your first place to go if something's not clear. And then if something's still not clear after watching those videos, then that's when you can post a message to the listserv, for example. Okay? So that's all I have to say specifically about the exam. Do you guys have any questions?
We download the TR program, download the software, T-I-N-N-R. Since we do not have this software in our computer.
I'm not for sure exactly what you're...
She doesn't
TINR?
you can download TINR.
Oh, you potentially could. I don't know if it will allow you to install, because there are security issues on these things on these computers, so that it prevents people from, let's say, installing some stuff that they shouldn't install. So I'm sorry that TINR is not on these computers. Or do you use TINR mainly? Yeah. You're going to take one test in this course. I think RStudio will be sufficient. I used to always make sure that all the computers in my classrooms had both TINR and RStudio. What I find is that, because since I can see what's on computer screens, very, very few students use TINR for an exam. They typically use RStudio, which basically I think means that most people use RStudio. I still think TINR is better, but I do not control these computers in this classroom, and it can be a pain. Maybe it's not the best word to use, but I'm going to use it. A pain to try to get changes made. Okay, so I'm sorry, but the two alternatives are RStudio and the program editor in R. Are there other questions? By the way, TINR used to be on these computers. I don't know what happened, why they removed them. Yes.
Let's say we need like a quick reminder of all the options for like the boot function. Can we use the R's help?
Yeah.
Okay.
So you can use R's help. Sorry if I didn't make that clear.
Okay.
Use R's help. In some of my other classes, what I've done is actually essentially put together a formula sheet, you could say, for the functions in R. I just decided not to this time, and I'm debating whether or not to continue doing that in my other classes. Because I think, in the end you can just type help. And I think it's actually beneficial to the student to be able to know how to use the R help rather than simply only relying on my formula sheet. Other questions? Okay. So again, what I will try to do is, get the assignments graded for you guys before the exam. I will at least have an answer key available for you. In the meantime, if you have any questions about the exam, please feel free to post to the listserv. I do check my email over the weekends, so post it there, and hopefully I can answer it in a reasonable amount of time. So, if there are no other questions, then we will continue in the notes. So we were talking about parallel processing. So, in terms of the actual statistics itself, like what we saw with the bootstrap, this section and then the next section is not very statistical. What we're essentially talking about is ways to do statistics, but a different way to take full advantage of the capabilities of a computer. And a few years ago, I got really interested in figuring out how to do this. I've always had an interest in it since I first saw someone do some parallel processing, a statistician do parallel processing around about the time that I graduated with my PhD. And through some various advances in R, and also the fact that there are now multi-core processors on all new computers, being able to do parallel processing is a lot easier. And the problem is that I think most students, and me until 3 years ago, didn't know how to take full advantage of it. So that's why I think this is a very important topic, because all of you are going to be doing stuff that probably will be somewhat time consuming at times, and you want to do stuff quickly so you can get an answer. So with respect to parallel processing, take a look at my handwritten notes here, and sometimes that's difficult because my handwriting is poor. Okay, so just to review a little bit here. So, within a CPU on a computer, so the CPU is what's doing all your calculations. So let's say that this is a CPU. You can have basically independent components of it that can control doing calculations. So for example, on my desktop computer in my office, my CPU has 6 different independent components called cores that can control how the calculations are done. So for example, on one core, I might be doing some, let's say, Monte Carlo simulations involving R. Another core, maybe I'm typing up some stuff in Word. And maybe on another core, I am, let's say, what would be a good example? Maybe I am listening to some good music. Okay? I still have 3 cores available to me that I could do work on. Since I have these cores here, these separate cores, that allows me to do calculations simultaneously at the same time without my computer slowing down. Before multi-core processors came out, if you were to, let's say, run let's say a Monte Carlo simulation on your computer, you would not be able to do essentially anything else while that would be running on the computer. Because everything would just be extremely slow because the computer is trying to do something on your processor, but then now you're asking for something else to be done. So multi-core processors were a rather nice invention, I guess you could say. I first started seeing them appearing in computers around 2006. Now, one of the big advances that we will see in technology that will be coming up is having programs that can automatically take advantage of the fact that there are multiple cores. So for example, has anybody used Adobe Premiere before to edit videos? Okay. Well, Adobe Premiere has the ability to take advantage of multiple cores. So maybe I might be doing some processing of a video, which can be very computer intensive, and maybe Adobe will be using 3 of my cores to process my video. And so thus you might expect then the video processing to be done a lot quicker than if it was only using 1 core. Now there's really not a whole lot of software packages out there that I know of, maybe I'm missing something, that has that capability yet. And so if you actually take a look at the Wikipedia webpage for parallel processing, you'll see there, basically there's a lot of open research problems out there to convert software packages or programs to automatically be able to take advantage of cores that are available, multiple cores. And so now, the reason why I bring that up is I want you to think of that in the context of what you do in statistics. As we've already discussed before, obviously Monte Carlo simulation can take advantage of multiple cores. But what else? Well, the bootstrap. Obviously, that's a Monte Carlo simulation. How about cluster analysis? For those of you who've taken Stat 873, you know that in cluster analysis you have to compare you have to calculate the pairwise distances between observations. If you have a lot of observations, that's a lot of distances. So if you have, let's say, 1,000 observations, it will be like 1,000 choose 2. Well, think if you have even more observations. So in all those 3 examples, Monte Carlo simulation, the bootstrap, and cluster analysis, what one would use is a type of parallel processing called embarrassingly parallel. Meaning, if we take a look at the Monte Carlo simulation, I kind of said this last time, what happens on essentially simulated data set number 1 is not going to affect what's going to happen on simulated data set number 2, it's not going to affect what's going to happen on simulated data set number 3, and so on. So, I don't know who came up with the term, but these are referred to as embarrassingly parallel. But there are other statistical algorithms out there that you can think of, like whenever you fit a model, maybe something that you did in Stat 971, which took a long time to fit a model. Think about how maybe you could use parallel processing in those particular cases. Now, often in fitting a model, let's say that you need a parameter estimate, let's call it beta hat. And at iteration 0, you come up with some initial estimate. Then you do some calculations, and at iteration 1, you get a new beta hat, and you compare the 2 beta hats. Are they close or not to decide on convergence? Well, if they're not, then you go to a next set of beta hats, and you keep on going until you reach convergence. But notice in this particular case, what happens on this iteration depends upon this iteration. So what I think is one of the big advances that will occur in statistics soon, not necessarily soon, but it will happen, is to figure out how we can reprogram in some of these statistical algorithms, like for doing maximum likelihood estimation, for fitting a model, doing some kind of optimization, reprogram them in so that they can take advantage of a multiple core processor and thus more quickly do the calculations. A couple years ago when I was at JSM, I saw the first set of people do that kind of stuff. And they were doing some stuff with what's called the EM algorithm to do this. And it's not just necessarily a computational strategy that one needs to figure out. It's also, you need to prove that indeed you still do get convergence. And so there is some mathematics that's involved too. So it's a nice merger of the mathematics of statistics with the computational side of statistics to try to do this kind of stuff. So, anyway, there's my introduction. Let's go back to the notes. Oops. Okay, so we talked about multi-core processors. We know the basic ideas of what a multi-core processor is. So, what are the 2 main companies that produce CPUs for a computer? Like what will be in these computers here? Intel obviously is one. Everyone knows about that. That's by far the leader. What's the other main one?
IBM.
Nope, IBM doesn't. I don't think that they necessarily produce it in large quantities for computers, like they did, I think, at one point. 3 letters. AMD. Okay. Advanced Micro Devices. Okay. Those are the 2 big ones. Now, the way that AMD and I like AMD's products. I've had 2 computers over the years that are AMD. The one that's in my desktop, the desktop in my office is actually AMD that has 6 cores to it. And the advantage of using AMD is that their products are typically cheaper. You're paying some extra stuff with Intel, for the name, essentially. There's a lot of other things that go into doing the comparisons between the 2, but I have no problems using AMD computers. Now, with AMD processors, basically how the cores are set up is exactly what I mentioned there. Okay, so you might have, let's say, 6 cores to a CPU. Now, for Intel, they'll also set it up like this, but they have an additional component. They have what are called threads. Each core will have 2 threads to it. And basically what a thread means is basically a set of computations. And each core of a processor for Intel chips can control 2 sets of computations at exactly the same time. AMD, you only have 1 thread per core. So what's the advantages of having 2 threads per core? Well, let's say you're doing some kind of R program, and R's running here, and for some reason R needs to wait for your computer to do something else. Maybe it's communicating with your memory that's stored, a memory chip. Well, while that processor's waiting, while that core is waiting, it's just kind of idle. And so what Intel does is says, okay, maybe we can take advantage of that core being idle and allow it to do some other kind of computation. So that's why there are 2 threads per core. Now, the actual time advantages of it, at least for what we will be doing, will be small, but there is still a little bit of an advantage. So it's important that you understand the difference between a thread and its relationship with a core. You'll see that as we go along. So, on the next assignment, what I will ask you to do is give me the specs for your computer. And I will want you to figure out, well, how many cores are on your processor, how many threads are available, what's your processor speed. So, again, this is a non-statistical topic, but you need to know that in order to understand how we can best use statistical methods on your computer or other computers. So we're going to take a look at some specs of computers that I have. So I have a Surface Pro 2 right here. Love it. I wouldn't buy any other laptop-like computer. And it has what's called a 4th generation processor, using what's called a Haswell architecture. It's an Intel processor. These 4th generation processors came out summer 2013, so they're still fairly new. And it has an Intel i5-4200U processor. It has 2 cores. Each of the cores run normally at 1.6 gigahertz. So that's what's often referred to as the clock speed. How fast it can essentially do, to some respect, its computations. It's more complicated with that, but that's one way we can think about it. But with newer sets of processors, what they do is they allow you to go higher if needed. So if I had an intensive Monte Carlo simulation that I'm running, my processor will actually run at 2.3 gigahertz typically. If my processor is completely idle, it will actually drop down to 0.9 gigahertz. The reason why this is being done to processors allow you to work at different clock rates is because the higher the clock rate, the more power it draws, the hotter the chip gets, the more then a fan needs to run, for example. And so, especially nowadays, we're very concerned about battery power and, how long you can go through the day without having to recharge. That's why these chips have been developed like this now, rather than being just at one constant gigahertz. I have Windows 8.1 on my computer, and so if I go under, so I can right-click on my little Windows symbol and go to my control panel and find System. You see a brief explanation of my computer specs. I know it's probably small, but it is, at least there's a screen capture in the notes. And so, for example, I have 8 gigabytes of memory. My first computer had 64 megabytes of memory. Got my first computer ever that I bought, 64 megabytes of memory. I told that to a good friend of mine who was also in grad school at the time with me. He said, "Why'd you get so much memory? What are you going to do with 64 megabytes?" Anyway, so this tells me also my processor that I have. Notice the 2 different speeds that are actually listed there. If I go under Advanced System Settings, and under the Advanced tab, Performance, oops, no, not Performance, what do I want? Hardware. Device Manager. So you have the various things that are installed on your computer, such as your mice, your monitors, network adapters, and you come down here to one called Processors. If I click on that, you see 4 things are listed. These are the 4 threads. I do not have 4 cores. I have 4 threads. So you can see how it can be kind of confusing at times. Also, let's go to my Task Manager. So Task Manager in Windows shows you, well, for example, what processes are being currently run. So if I come down to here to my, my bar down here, and if I go to Task Manager, look under Performance, you see some information about how my computer is running right now. So for example, I have 2 cores, 4 logical processors. That means I have 4 threads. So essentially your computer can try to take advantage of 4 processors even though it doesn't have 4, it can take advantage of 4 cores even though it only has 2. It can basically have 4 sets of computations going on at the same time. We can see what my speed is right now. I'm not really doing anything on my computer. That's why you see this low there. Notice utilization says 25%. I'm using 1 core right now out of 4. I have 4 threads available. Let's explain it this way. I have 4 threads available to me. 1 thread is being used right now. And you know what's being used by? I'm recording the presentation. Not presentation, I'm recording the class. And you can see it's not necessarily taking up a whole lot. It's not even requiring to go all the way up to 1.6 gigahertz. And so that gives you some information. For those of you who have Macs, sorry, I'm not for sure exactly how to get to that. If you can't figure out how to do it yourself, pick your favorite Windows-based computer and tell me about that computer instead of your own Mac eventually on your eventual assignment that you'll have. Okay. Now with each processor, once you figure out its name, you can Google it, and we'll take you to Intel or AMD's website. And so I went to Intel's website for this one, and you can see what I have circled there, 2 cores, 4 threads. You can see that the processor came out in 2013, Q3. You can also see some information about clock speed. Now, there will be 2 main packages in R that we will look at to do parallel processing. There's actually a few other ones. We will look at 2 main ones. The first one that we will look at is the one called parallel, because that comes with now the default installation of R. And there is a function in the package called detect cores. And if you run it with all the defaults, it tells you how many threads you have available to you. If you use the argument logical equal false, remember how we saw the word logical processors? a few minutes ago. If you say logical equal false, then you have the actual number of cores returned back to you. Okay. So let's take a look at another one of my computers. This is actually one I don't really use much anymore. It's my Fujitsu tablet PC. One reason why I wanted to use this one here is because it actually uses a 3rd generation processor. So we had looked at a 4th generation processor. This one looks at a 3rd generation processor. As you might expect, it's probably not going to be as good, even if it has a higher clock speed with it. I would imagine that there's probably some of you who still have laptops or computers that have 3rd generation processors in them. They use what's called the Ivy Bridge architecture to them. And I have 2 cores that each run at 2.4 gigahertz. Now, in order to get the specs on my computer, I have Windows 7 on this computer. I give you some directions about how to get the specs, and you're going to see something that looks like this. And again, you'll see the actual processor name at some point. You can also, it will tell you how many cores you have. If you Google the processor name, it takes you to, in this case it was an Intel processor, it takes you to Intel's website, you get the same kind of information that we saw before. Also, with my Dell desktop computer, I purchased this in August 2011, so it is kind of old now. But at the time, it was essentially top of the line in terms of its processor. I purposely purposed an AMD processor at the time because it had the most cores that were available. At the time, 6 was the most. I think now, just for a regular like desktop, you can get maybe 10 cores, I think. And so it was an AMD processor, where each core ran at 3.2 gigahertz, 6 cores, 1 thread. And so if I ran the detect cores function, you see the results. Lastly then, this will be our first introduction to the actual supercomputers that we have on campus. This is, I think, show you why they're called supercomputers. And so there are going to be 2 main supercomputers that we're going to look at. One's called Crane, one's called Tusker. Crane's the newer one, but Tusker is still very good and it has some advantages to it. And from the actual Holland Computing Center, that's the people that, or the group that controls the supercomputers on campus, from their website, you get information about the processors that are in those computers. So the Crane uses Intel Xeons, and they run at 2 gigahertz apiece for each core. Notice, well, let's also talk about Tusker. Tusker uses AMD's Optitron. They run at 2.1 gigahertz. Now, the way that they have their computers organized over there is that they basically have what are called nodes. And nodes you can think of as, let's say, maybe one of your computers here. But instead of just having one CPU, you could have multiple CPUs. Okay, so not just multiple cores per CPU, you actually have multiple CPUs. So with Crane, it has 2 CPUs per node. And each of these CPUs have 8 cores apiece. So there are 16 cores that are available to you on one node. With Tusker, they use the and also these would have the 2 threads as well per core. With the Optitron, they have 4 CPUs per node, and each of those processors have 16 cores. So there are 64 cores per node. Now look at how many nodes that are available. So take 16 times 106, and so you can see there's a lot of cores that are available to you. Take 452 times 16, again you can see there are over 4,000, more than 4,000 cores that are available to you. This is why this is called a supercomputer. We'll look at some other supercomputers once we get to the high performance computing section of the course, and you will see that there can be lots and lots and lots more nodes and cores available. Okay, it's 12:15. Are there any questions?
Can I ask you a real quick question about the assignment?
Yes.
Okay.
I'm sorry. I thought I had it available.
Yeah, I know I missed my chance. But
Okay.
when it says plot the observed value of t beyond
Mhm.
the histogram, is that gonna be the same for every single, problem?
When I say observed value of t, I'm talking about t itself, not t star.
Right, so just from the original,
From the original sample.
Okay.
So there should be always one t that's plotted, similar to how we had one x squared on those bird example
Okay.
plots.
Okay.
Okay? It's just to allow you to visualize how extreme your observed statistic is.
okay.
Any other questions? Okay, that's it for today.